This video is the first in a multi-part series about the Helios radiation model. In this first video, we'll cover the basics. So how does the model itself work and how is it different from other ray tracing based radiation models that may be used in 3D plant modeling or other applications. The main difference between the Helios radiation model and traditional ray tracing models is how the actual ray tracing is handled. And there are two general types of ray tracing formulations. We have forward ray tracing and backward ray tracing. In forward ray tracing, we essentially trace the radiation as it leaves various sources and then trace it as it moves throughout our domain. In the event that that radiation intersects some object, we then trace the scattered radiation that may be reflected or transmitted through that surface. So it's very intuitive in that you're essentially tracing the radiation as it would propagate in the environment. So this is an advantage of this approach. It's intuitive, it's fairly straightforward to conceptualize. Also, when it comes to dealing with scattering, it's much easier to formulate because you just trace the radiation as it would propagate in reality. There are some disadvantages of this approach. One is that you can get poor ray sampling when you have small or occluded elements. Because you're tracing the radiation from the source to the elements, you're relying on the radiation beams to actually reach and sample individual elements. So because you can't use an infinite number of rays or beams in your simulations, then when you have a really complex mesh with a lot of occlusion or small elements, then you often get poor sampling when you use a forward ray tracing approach. This has led to the formulation of backward ray tracing approaches. Both of these have been used for many years in both computer graphics as well as environmental ray tracing simulations. In a backward ray tracing approach, we trace the radiation from the object back toward the source, so in the opposite direction as previously. So we launch a ray, sample it at some position along the object, and then trace it back to one or more sources. From this, we can calculate the amount of radiation that was absorbed by that object. And when it comes to the direct radiation part, it really doesn't matter which direction we trace it in. If it is occluded or hits some object, then that's going to happen regardless of the direction in which you trace the radiation. The complication with this comes into play when we want to deal with scattering of radiation, or as we'll talk about here in a second, emission of radiation. So in backward ray tracing, it's essentially iterative, and we'll elaborate on this here in a second. But we need to still sample and trace that scattered radiation somehow. And how we deal with that is a main aspect in which different methods contrast from each other. So the advantages of this approach are that you get guaranteed ray sampling for each element, even if you have very small or occluded elements. Because you're launching your rays from the objects, it guarantees that they are adequately sampled. The downsides are that it's more difficult to formulate. It's more difficult to kind of understand how it's working because you're not tracing in the natural direction as you would think about it for radiation propagation. It's more difficult to handle scattering, as I mentioned. And how do we handle emission if we want to calculate emitted radiation from these elements as well? Next, I'll go through the general process by which the Helios radiation model does backward ray tracing and handles these different issues. So the first part is fairly straightforward. We already kind of talked about it on the previous slide, but we start with an initial ray launch, and this gets our incident radiation. So we, again, sample various points on the element stochastically, and then we send many rays back toward the different sources that we have in our domain. And then from this, we can calculate our incident radiation. So the amount of radiation that would be incident on this element, not dealing yet with scattering or absorption or those more complicated aspects. If we have some occlusion, like part of the source is blocked by another element, then this will be naturally handled within the backward ray tracing approach as well. So next we need to partition that incident radiation. Some fraction of that radiation is going to be absorbed, some fraction will be reflected, and some fraction will be transmitted. The fraction that is reflected is described by our reflectivity, which we usually assign the symbol rho, and some fraction will be transmitted. We quantify that based on our transmissivity, which is denoted by the symbol tau. And then anything that's left over is what's absorbed. We don't specify an absorptivity directly in Helios. It's just 1 minus the reflectivity minus the transmissivity. So the user specifies reflectivity and transmissivity, but not absorptivity. Here's just a simple example. Let's say that we have our two primitives here. One of them has an incident radiation of 1,000 in arbitrary units. The other has an incident radiation of 500. Let's say that their reflectivity and transmissivity are both 0.25. So for primitive 1, we would have an incident of 1,000. So then 25% of that would be 250. So that could be our reflected. Same thing for transmitted. And then whatever's left over is what would be absorbed. So 500. You could apply the same thing to primitive 2. And different primitives might have different incident radiation fluxes, both based on their angle. If they're at a sharper angle relative to the sources, their flux is going to be lower. This could also be due to occlusion. If part of the primitive is sort of occluded or blocked from the view of the source, then its incident flux could be lower. Now, the absorbed part is relatively straightforward to deal with. We just kind of deposit it into that primitive and say that that's absorbed energy. But this reflected and transmitted energy has to actually be traced or tracked as it is transferred throughout the domain. So we call this to be scattered energy that we need to now deal with. We track this scattered radiation iteratively. So in our first iteration, what we would do is we would sample multiple points along the surface of our primitive, and then we would sample multiple directions. And from that, we would do a ray launch starting from our primitive and then casting out into the domain. And if one of those rays intersects another primitive object, then we're going to sample that primitive's to be scattered radiation. So we're not casting out the energy, we're not tracing that scattered energy in a forward sense. We're casting out a ray, and then whatever that hits, we're going to sample its radiation and then potentially absorb that radiation back in our primitive. So this is the difference, again, between the backward and the forward ray tracing. So let's say that based on this previous example, we did this scattering trace, and we found that there was, for our primitive 1, 8 units of radiation incident just due to scattered radiation. We found before that due to direct radiation, our incident was 1,000. Let's say that our incident is now 8 units. This is radiation that when those rays were cast out from our primitive, it detected or found 8 units of radiation that would have been scattered back to our element. And then we need to again partition that between reflected, transmitted, and absorbed radiation. So if again we have a reflectivity and transmissivity of 0.25, then we'd have 2 units reflected, 2 units transmitted, and 4 units absorbed. And something similar could happen for the other primitive. Again, we have some energy that needs to be traced. This is now reset as our to be scattered energy. You notice that the amount of energy to be scattered is much lower than what we had before as far as just our direct incident. And this is usually true. We find that the amount of radiation that needs to be scattered decreases exponentially for each of these scattering iterations. And this is both because we've got some radiative properties that are typically much less than 1. So our scattered radiation is a fraction of the incident, and just the fact that we have some view factor of other elements that may be less than 1 as well. So these factors kind of multiply by each other, so we get this exponential decrease in this to be scattered energy. We could continue doing this trace iteratively until we have an arbitrarily small amount of radiation left to be scattered. And how many iterations you want to run is up to you, depending on how accurate you want the result to be. If you want very accurate scattering such that we have very small amounts of radiation left over at the end, then we would want to run multiple scattering iterations. If it only needs to be a little bit accurate and you don't really care about the scattered radiation so much, or if there's just not a lot of scattered energy to begin with, let's say that our reflectivities and transmissivities are small, then we could get away with only a few scattering iterations. It just all depends on your particular application. And depending on how many scattering iterations we want to run, at the end, let's say that we want to run 3 of them, at the end, there's always going to be at least a tiny bit of radiation left. And so at the end, the model just basically deposits that on our element and doesn't trace it again. If that amount of radiation is small, then this has a negligible impact on the end results. And so what about long wave emission? How do we deal with reverse ray tracing for long wave emission when our primitives are actually emitting radiation from them and this is being cast out into the domain? If we were using a forward ray tracing approach, we would calculate how much radiation needs to be emitted using Stefan-Boltzmann law, and then we would cast that radiation out into the domain. But using this backward ray tracing approach, we essentially treat it the same as we did our scattered energy, except for instead of sampling that to be scattered energy, we sample the emitted energy. So we again sample points on the surface of our primitives, and then we sample ray directions, and then we cast out those rays, and then if those hit some object, then we sample its emitted flux, and then use that to calculate the absorbed, transmitted, and reflected radiation based on our radiative properties. And again, we can continue that iteratively until we have a negligible amount of radiation left over. So this is the main difference between the Helios radiation model and other radiation models. You can read about it in the paper that's cited at the bottom in ecological modeling. What we show in that paper is that especially for emission, using this backward ray tracing approach is really important, particularly when you want to couple it with the energy balance equation, which we'll talk about in future videos. Because even small imbalances in the long wave emitted flux can create large errors in your energy balance equation and give you unrealistic temperatures no matter how many rays that you use. And we kind of illustrate this in the paper using a fairly simple example. In Helios, when we go to run our radiation model, we need to specify some parameters related to the ray trace. One of those is the number of rays that we want to launch per element. So we talked about sampling points on the surface of the primitive element. This is a parameter that we can choose. We can increase it if we want a more accurate simulation. The trade-off to that is that it's going to take longer to run the simulation when we have more rays. And the runtime increases almost linearly with the total number of rays in our simulation. So if you take the number of rays per element and multiply that by the total number of primitive elements in our domain, then this is going to give us a rough estimate of the scaling of the runtime of our simulation. In the ecological modeling paper, we show the scaling in terms of both the accuracy and a little bit about the runtime. So the error in the simulation tends to go down exponentially with the number of rays that we use. And this plot is showing the difference in that scaling when we use a forward ray tracing approach or a reverse ray tracing approach. So we can see that we're an order of magnitude or two lower in the error at any given number of rays. And then we get kind of similar scaling as we increase the number of rays, but we get a substantial offset between the two. So for a given number of rays, the reverse ray tracing approach tends to be substantially more accurate. The error also decreases exponentially with the number of scattering iterations. So we have a plot in the paper that shows this. Usually you can get away with maybe 2 or so scattering iterations. Somewhere between 1 and 3 is typically what you want to use for a normal environmental simulation. If you're trying to get, say, remote sensing measurements out of your simulation using the radiation camera, sometimes it's necessary to have more scattering iterations to get a very accurate answer because you may be dealing with very small reflected fluxes in that case, and you may need more scattering iterations to get an accurate result. In the model, we have 5 different types of direct radiation sources. We have a collimated radiation source, which is meant to simulate the sun. So collimated means that all of the beams of radiation are perfectly parallel to each other. In contrast to that, we also have a sun sphere radiation source. This is essentially a sphere with the same radius and distance from the Earth as the actual sun. So this gives us penumbral effects because the beams of radiation are not exactly parallel to each other. There's a little bit of difference in the angle of the beams of radiation, and that allows us to simulate penumbral effects. In most cases, unless you have a really tall canopy or something like that, the difference between the collimated and sun sphere source is very small. Just looking at this visualization here of this Stanford bunny, which was about a meter tall or so, you can see almost no difference. If there was a strong difference, you would see kind of a little bit softer shadows on the edge due to the little bit of penumbra that forms within the shadow. When we're doing simulations to, say, compare against simplified models like Beer's law-based models, for example, we'll usually use the collimated source because this exactly matches the assumptions of those models. But for any type of environmental simulation, it's probably best to just use the sun sphere source because it will get those penumbral effects if they are present. And there's really no computational cost difference between the two. Then we have 3 different sources that typically correspond to artificial lighting. So we have a sphere in which you specify its position and its radius. We have a disk in which you specify its position, its radius, and its direction. And then you have a rectangular source where you specify its position, its width and length, as well as its direction or angle. So we can use these to simulate things like lamps or LED light arrays or things like that. One very important detail with the Helios radiation model that is a common source of error, particularly for those that are not used to working with 3D type simulations, is that when we specify the fluxes emitted from these sources, we always specify the flux perpendicular to the direction of the source rather than perpendicular to a horizontal plane. Most times when we're dealing with simplified models like 1D or bulk models of canopy radiation transfer, we almost always use the flux that's perpendicular to a horizontal plane or the ground. And that's often because this is what we might measure if we put out a radiation sensor that's leveled to get the incoming flux. But in a 3D model, this horizontal flux is not really relevant because we've got these 3D objects and you've got surfaces at all different directions. And so we want to specify that flux perpendicular to the source, and then it will calculate the incident fluxes based on the angles of all other objects in the domain. These two are related to each other based on the cosine law. So if we denote R0 as the flux perpendicular to the source and theta s as the angle between the source direction and the horizontal plane direction, then we just multiply that R0 by cosine of that zenith angle between the horizontal and the source, and we would get the flux on a horizontal plane. So we could relate these two to each other. The problem with that is that when the sun or the source direction becomes close to horizontal, then cosine of theta s goes to 0, which means that R0 blows up to infinity. So when the sun is near the horizon, for example, using this relationship becomes a bit problematic. So what we do in Helios most of the time, and we'll talk about this in a future video, is that we use a solar flux model and we just calibrate it based on measurements if we have it. We can just predict what that flux is perpendicular to the sun direction if we don't have any measurements, if it's just a theoretical or hypothetical simulation. If we have actual data, then we just calibrate that model based on the data, and then we can predict what that flux is perpendicular to the sun, regardless of what its direction is. If it's one of those finite shaped sources like a disk, for example, then this is more intuitive that we would specify the flux that's emitted normal to that surface. It wouldn't really make sense to specify the flux horizontal to the ground in that case, because when the angle of that source moves, then that flux would also change. Just think about it that we always want to specify the flux as perpendicular to the surface of the source, which may also be the direction of that sunlight propagation in the case that we have a collimated or sun sphere source. We can also simulate diffuse or ambient radiation within the Helios radiation model. Diffuse radiation originates from the sky in all different directions, and this can originate due to two different mechanisms. One is it could be due to solar radiation that was scattered by the atmosphere before reaching Earth's surface, so it's no longer in that same direction of the sun, but it's been scattered into a different direction. We can also get an ambient or diffuse flux in the long wave due to emission from atmospheric molecules. So if we're not in the solar wavelength range, but we're in the thermal infrared range, we'll also have some diffuse radiation that emanates from the sky. And this diffuse radiation from the sky in the long wave is super important. If you set it to 0, then you get huge imbalances in your long wave radiation budget, and it will throw off any subsequent energy balance simulations or anything else that relies on it. By default, Helios assumes that the ambient radiation is isotropic, so that means it has equal intensity in all directions. If you were to take a horizontal surface and change its inclination, the diffuse flux would be the same regardless of its direction if we have this isotropic diffuse radiation. But we have the option to change that to specify some anisotropic distribution of the diffuse radiation. If we're talking about solar diffuse radiation, it is usually highly anisotropic. It's usually concentrated in the direction of the sun. If we have very cloudy conditions, it will approach more of an isotropic distribution. But for clear sky distribution, it's going to be very anisotropic. And Helios has a model for specifying that angular distribution of that diffuse solar radiation. When we're simulating visible or solar radiation, we usually want to think about this in terms of discrete wavelength bands. We usually don't simulate the entire solar spectrum at once, but we break this up into multiple bands. And the reason for that is because the radiative properties of our objects are typically quite different across different wavelength ranges. So if our radiative properties vary with wavelength and our source flux distribution varies with wavelength, we're going to get a more accurate simulation if we break up our simulation into multiple wavelength bands. This shows a typical reflectance and transmittance spectrum for a leaf. So we can see that it varies quite a bit with wavelength. When you're in the photosynthetically active region, leaves are quite good absorbers. They don't reflect or transmit very much radiation. In the near infrared, they are not very good absorbers, and for good reason, because that absorbed radiation typically just contributes to heating up the leaf and doesn't contribute much in terms of photosynthesis or other biophysical processes. It's common when simulating shortwave radiation in vegetation to use a two-band approximation, where we break things up into the PAR or photosynthetically active radiation region and the NIR or near infrared region. And usually we assume that the PAR is somewhere around 400 to 700 nanometers, and the NIR is 700 up to 2500 or so nanometers, or essentially the rest of the solar spectrum. Above 2500 nanometers or so, there's not much solar radiation left. So this makes sense because we can reasonably assume that our radiative properties are constant across these regions. We can see that they're definitely not perfectly constant. If we wanted a really accurate simulation across these regions, then we want to further break these up into more wavebands. Typical values for leaf reflectivity in the PAR are around 5 to 10%, and in the NIR somewhere around 40 to 45%. Transmissivity values are pretty similar to reflectivity values in this range for leaves. For soil reflectivity, it can vary quite a bit, but maybe somewhere around 20% in the PAR and somewhere around 40% in the NIR. and we assume that the soil transmissivity is 0, that it absorbs all the radiation in the region that we are interested in. In the Helios radiation model, we have the ability to specify different behavior as far as the different faces of a primitive element. Primitive elements are planar, and so they have 2 faces, and we may want to control how those different faces behave when it comes to radiation transfer. For example, if we have our ground just represented by a bunch of patch elements, we don't want them to absorb radiation from the backside. We just want them to be one-sided such that we concentrate on what's going on the upper side. And for diffuse radiation, we actually get diffuse radiation coming from all directions, even up from below. This is necessary for consistency so that we don't get weird edge effect inconsistencies. We essentially need the diffuse radiation to encapsulate the full sphere. So this means we don't want our ground to be absorbing radiation from the bottom. We want it to just still block that radiation, but ignore any absorption coming from the bottom. So we have this primitive data value called two-sided underscore flag. It has a data type of unsigned integer. And based on how we set this value, we can control how the different faces of the primitive behave with respect to radiation absorption. So if we set this value to 0, then our surface only absorbs and emits radiation from the upper face, and any radiation hitting our back face is blocked, but it doesn't contribute to the absorbed fluxes. So for the ground, we usually set its two-sided flag to 0. By default, if you don't set this at all primitives are set to a value of 1. In this case, we have a two-sided element. It can absorb and emit radiation from both sides. There's a special case value of two-sided flag that was added a bit later. This is a value of 2. If you set the two-sided flag to be 2, this basically turns your primitive into a sensor. And this means that it measures any radiation that passes through it, but it doesn't interact with the radiation field. It doesn't absorb radiation. It doesn't scatter any radiation. It just becomes essentially a passive sensor that doesn't block the radiation, but just measures the radiative flux passing through it. You could also use this if you weren't really interested in treating the primitive as a sensor, but you wanted it to be invisible to radiation. You would set its two-sided flag primitive data value to be 2. We can also enforce periodic boundary conditions within the Helios radiation model. So let's say that we wanted our canopy or our geometry to repeat indefinitely in all directions so that we could avoid edge effects. We could use a periodic boundary to do that where it doesn't increase the computational cost of our simulation, but then allows us to simulate very efficiently this infinite expanse of objects within our domain. We can think about this like drawing a bounding box that encapsulates all of the elements within our simulated domain. And then when we launch those rays, which originate from inside that box because we're using backward ray tracing, if that hits a periodic boundary, then it will just recycle it back to the other side of the bounding box and then continue on. And so this effectively simulates what would happen if you had that box infinitely repeating in all directions. We can have a periodic boundary just in the x direction or just in the y direction, or we can have it in the x and y direction. And this is specified using this enforced periodic boundary method within the radiation model that we'll illustrate through examples in a future video. I'll talk about this in a future video, but the biggest source of user error when using the periodic boundary conditions is you need to make sure that your ground extends further in the horizontal direction than any other of your elements above. So you don't want, let's say, branches that are kind of hanging over the edge of your ground. In that case, it's going to take a bounding box, but then you're going to get kind of this gap in your ground. You want your ground to be the widest object so that it forms this solid plane in your repeating domain. Otherwise, you'll get light that can leak, diffuse light that can leak up from those gaps in your ground if you don't have it extending further than any other objects above. Before we get into the code examples, I just want to touch briefly on some of the verification and validation that's been done on the model. This is a common question that people ask. I would say the radiation model is the most well validated out of all the plugins within Helios. We have many different ways of verifying and validating that the models are working. One is to use toy problems where we know what the exact analytical answer is, and we can use that to compare against to make sure that we're getting very close to that exact analytical answer. So some simple geometries where we have exactly known view factors, like from a radiation textbook. We have a case for a gas-filled furnace to simulate the interaction with a turbid medium. We can simulate a homogeneous canopy and compare against the theoretical result from Beer's law. And we have currently about 15 or so different toy problem cases. These are in the self-test routine within the radiation model. And every time that the code gets checked in to GitHub, it runs through these different tests in order to verify that the model is working correctly for all these different cases. Now, the strength of this is that we know what the correct answer is, so we can check against that. But the downside is that they're still fairly simple example problems. So this is more of a verification than a validation, because it doesn't really say how well we're able to, for example, represent radiation transfer in a complex vegetative canopy. To verify the radiation camera model, we've done some comparisons against the ROMC and RAMI cases. These are benchmark cases where you'll compare many different models against each other to get an idea of what are typical values that we should end up getting from our model. These have some very complex cases with realistic geometries. So this is an advantage of this approach. The disadvantage is that we don't actually know what the correct answer is. We just can compare against other models. And so our skill is just relative to other 3D radiation models. And Helios typically kind of falls in the middle or is close to the benchmark case, depending on the case that we're looking at. We've also done field validation to actually compare against what we consider to be reality, as exemplified by field measurements. So Alejandra in the lab specifically has been doing a fair amount of work in verifying the radiation model. These are some results for a vineyard where they put out a radiation board with an array of radiation sensors on the ground to measure transmission through the canopy. We've also done this in an orchard. In a previous paper, we looked at validating temperature predictions, which kind of integrate both shortwave and longwave emission calculations within the model. So you can take a look at that paper for some examples on the energy balance validation side. All right, let's jump into some code examples so we can illustrate how to set up a basic radiation simulation. I've already gone ahead and created a project. If you have not already seen the video on how to set up a basic project, I would recommend going and checking that out first. Just wanted to point out our cmakelist.txt file. I've set the executable name to radiation part 1. I've also made sure that for our plugins, we've included the visualizer as well as the radiation plugin. In my main file, I have included the header for the visualizer, which is visualizer.h, and included the header for the radiation model, radiationmodel.h. I don't need to explicitly include the context.h header because it's included in both the visualizer.h and radiationmodel.h files. I'm using the Helios namespace. I'll not use the standard library namespace just so that we can be explicit about specifying those functions and data structures. So what we're going to do in this coding example is we're going to load in a 3D model from file. We'll just use one of the PLY models that's included with Helios. You could use any model that you want or use a different plugin in order to create some geometry that you might be interested in. We'll just use this for simplicity. So we'll start by defining an instance of the context. I'm going to call it lowercase context. And then we can use the load PLY method to load our model from file. We'll just go with the basic version that just takes the path to where that model is located, The one that I'm going to load here is in the ply directory. We're going to load the stanforddragon.ply. So if you remember the golden rule of specifying file paths in Helios and more broadly C++, it's always relative to the directory in which I'm running my executable. I'm running it in this build directory, so I need to go up 3 directories to get to the base Helios directory, and then into this ply folder, and then I can type stanforddragon.ply. There's an overloaded version, or there are multiple overloaded versions of this load ply method. We're just using the basic one. You could use it to specify the location of your object or apply some scaling or rotation. We'll just go ahead and apply the defaults. In our model, we're also going to want some type of ground that our model is going to be sitting on. So I'll use the add tile method in order to do that. And our first argument is going to be the location of our tile center. And so we can just put that at the origin. I can type null origin, or you could type make underscore vec3 and then 0, 0, 0. This is just a shorthand. The second argument is a vec2 that's going to give the size of our tile. So I can use make vec2 here, and I'm going to make it 0.25 by 0.25. Our third argument is going to be a rotation of the tile. If we just type null rotation, it will apply no rotation. And then the last required argument is going to be the number of subdivisions on our tile. This is an int2, and I'm going to make it 250 by 250 subdivisions so we get pretty good resolution within our tile. Now let's just go ahead and visualize what we've got so far. You can use this macro that I talked about in a previous video if you've loaded the Helios configurations into CLion. So if you type exclamation point visualizer context, it'll pull up a basic setup for just visualizing context geometry. You could also just type this out manually. One addition I'm going to make is I'm going to change the lighting model so that we can see a little bit of contrast in our image. So I'll type visualizer dot set lighting model, and then I'm going to set it. We have to type this visualizer : and then a lighting model. I'm going to do lighting Fong. Don't forget your semicolon at the end. And then I can go ahead and run this just to see what we're dealing with so far. And the Stanford Dragon model is pretty heavy. It's got almost 1 million primitives in it. So it's going to take a little bit longer for your program to run, especially I'm in the debug configuration here. And so it's going to be even several times slower. So if you want to use a lower resolution model like the Stanford Bunny or some other model just so that it runs faster, then you can feel free to do that. I just wanted to use the Stanford Dragon for this example because I think that it looks nice. All right, so we've got our model here. You can see that we're sort of looking at the backside of our model. But if you rotate it around, you can kind of see it from different angles. Just so that we can get practice with rotating things, I'm going to go ahead and just rotate this in our code so that we don't have to manually rotate it using the arrow keys. Again, I'm just using the left and right arrow keys in order to rotate my model. We could rotate the camera by 90 degrees, or we could rotate our entire model by 90 degrees so that we're looking kind of to the side. Let's just get some practice with rotating objects or geometry within our code. So I'm going to just rotate the entire PLY model. And there's multiple ways you could do this. We could use the overloaded versions of the PLY method, which has an argument that allows us to apply a rotation directly as we're loading it. Since we're going to need it later, let's just go ahead and assign the output of this call to a vector of UUIDs, and then we'll use the context in order to rotate it. I'm going to assign the output of this and store all of the UUIDs from it. So I'm going to need to make a vector of uints. And then I'm going to give it some name. Let's call it UUIDs dragon. And then assign it to the output when it calls this. So this is going to load almost 1,000,000 triangles into the context, and then we're going to assign that same number of UUIDs into this vector. So this vector contains the identifiers for all of the triangles that were just loaded from this call. And then once we have that, we can modify it any way that we want. So let's call context.rotate primitive. And then our first argument is going to be that vector of UUIDs. And then our next argument, there are several overloaded versions of this method to rotate our primitive. We're going to rotate about the z-axis going through the origin. So if you imagine a vertical axis that passes through the point 0, 0, 0, we're going to rotate about that axis. So first thing we need to specify is the angle about which we want to rotate. We always specify these angles in radians, but I can use the deg2rad function built in to Helios in order to convert that if it's easier to kind of think in terms of degrees. So I'm going to rotate it by 90 degrees. And then I need to specify an axis. I'm going to rotate about the z-axis. You can also specify an axis in terms of vec3 to do an arbitrary axis. I can also change the origin about which I'm going to rotate. So if my object was displaced, say, by 1 meter in the x, then I could move that axis by specifying an additional argument to this function here. So now let's go ahead and visualize again just to see where we're at. So now we can see we're looking sort of to the side of our model instead of from the back because we just rotated it by 90 degrees. Now that we've got our geometry set up, let's go ahead and actually run the radiation model. So there's also a macro built in to add a band to our radiation model. You can also just type it out manually. So I type !radiation basic, and it'll just fill in a basic band for me here. I'm going to go ahead and rename it to be par instead. So here what this code is doing is it first adds our radiation band. As we mentioned before, we always need to define explicitly which bands that we want to load here. Since this is going to be a shortwave band, I want to disable emission in this band. So we can call disable emission. And then we need to give it the label of our band, which we decided to call it par. At this point, the fact that I called it par doesn't mean anything. It's just a label. I could have made up any label that I want. This is just what we've given to it. And then as we set the attributes of that band, that's what's going to make it to be something corresponding to a physical radiation band that you might observe. But for now, it could be anything. So we've disabled emission. Now we have no sources of emission in our scene. So let's go ahead and add one. So I'm going to add a sunsphere source. So we can do radiation, add sunsphere radiation source. And this call is going to output an unsigned integer, which is the identifier for our source when we want to reference it later. Let's say that we want to change its direction or set its flux. So we need to assign this to a variable. So I'm going to assign it to an unsigned integer. Let's call it sunID. We can use that to reference it later. When we call it with no argument here, it's just going to set its direction to be vertical by default, but you could use the overloaded version and change its direction. Now let's set its flux. So I can call radiation.set source flux. And we need to first give it an ID to a source. We just called that sunID to the source we just added. If we have multiple sources in our domain, like if we have a bunch of rectangular LED sources, for example, then we might have multiple IDs to deal with that may have different fluxes. Now we need a label for a radiation band. We called ours par. And then we need a flux. And I'm just going to choose 500 for our flux here. So then we always call update geometry. And once you've done that, you generally don't want to change other things about our geometry or some settings. It's going to go ahead and assign any radiative properties if we have them, and then reconfigure all the geometry. And then once we call this run band, then it's going to go ahead and run the ray trace for that particular band. And let's change our visualization here so that we can visualize based on our computed radiation field So I'm going to go back to the default lighting model that doesn't apply any lighting within the visualizer itself. We'll have obviously some lighting within the radiation model, but what we want to do is visualize based on the flux that's computed. So it's going to calculate the absorbed radiation flux for all those primitives, about 1 million triangles in our model, and then we want to visualize based on those. And so there's a method here called color context primitives by data. In this case, we can apply a pseudo color mapping within our visualizer based on some primitive data values. And what we want to add here is that absorbed radiation flux that's computed by our radiation model. It's complaining here because I need to give it the label for primitive data that we're going to visualize based on. So if I pull up the documentation for the radiation model plugin, it's going to tell us what the output primitive data that it's writing is. So for every band that we added, it's going to write this output primitive data called radiation underscore flux underscore, and then the name of any radiation bands that we added and ran within the model. So because we have a band called par, it's going to create primitive data called radiation underscore flux underscore par. So this is the primitive data that we want to use for our visualization. So we do radiation underscore flux underscore par, and it's going to do a pseudo color mapping based on those absorbed flux values. So we should be ready to go ahead and run our simulation. And here we have our visualized radiation field. You can see our color bar that tells us the flux that each color corresponds to. You can use your left and right arrows or up and down to go ahead and rotate the model to see our computed radiative fluxes. And again, we didn't specify a direction for our radiation source. It's just perfectly vertical overhead. So let's try changing the direction of our source. We can get a little bit different perspective and get some practice with changing that value. There's a method here called set source position, and we can either specify that in terms of a vec3, so a vector telling us the direction and possibly position of our source, or a spherical coordinate to specify the direction of our source. Since we're using a sun sphere source, there's no position to be set in terms of absolute position. We only set a direction. So if we were, say, adding a rectangular source, then the actual position that you specify here would matter. So for example, the radius in the spherical coord or the actual absolute XYZ position that you specify with a vec3. Here we only specify direction, so any vec3 that we specify, it's going to just take and normalize it and just take a unit vector in that direction. And if we specify a spherical coordinate, it's going to just ignore the radius value. So we need to give it the ID to our source. That was sun ID. And then let's go with a spherical coordinate. And we can specify an elevation angle and an azimuth angle. These need to be specified in radians, as we said before. Let's use deg2rad. I'm going to set our elevation to 40 degrees, convert that to radians, and then our azimuth to, let's say, 45 degrees. And then we can go ahead and run that again. And here's our new simulation with our sun angle elevation of 40 degrees and azimuth of 45. So you can see we now get this shadow that's cast out to the side of our model. We notice that the shadow actually goes off of our ground area here. It's kind of getting cut off. We could obviously make our ground bigger so that that doesn't happen, but let's use this as an opportunity to take a look at the periodic boundary condition. So we could imagine a case where we have an infinitely repeating array of these dragons, and so maybe we want to apply a periodic boundary condition so that the shadow will kind of be cast back onto this part of our patch that we already have. All we need to do is call the enforce periodic boundary. And then let's give it an argument of xy. So it's going to apply a periodic boundary condition in the x and y directions at our semicolon, and then we can rerun. And here's our simulation with periodic boundary conditions. We can see that the shadows that left the edge of our ground here are getting wrapped around to the other side. So here's the part on this axis that's wrapped around here. And then we've got a little part at the top of the dragon's head that's being wrapped around to the other side here. And just to reiterate the point that was made earlier in the video, we want to make sure that our ground is the widest object in our domain whenever we're using a periodic boundary condition. We wouldn't want, say, part of the dragon's head to be hanging over the edge of our ground, because then that's going to create a gap in the ground. It basically takes a bounding box around the whole domain and then uses that to create the periodic boundaries. So if you have some object hanging over, then you're going to get the bounding box that touches against that object. And then if that object is not the ground, you're going to get a gap in your ground. Also, this is a bit of a silly example with our dragon here. You wouldn't want an infinite array of dragons probably, but if these were trees, for example, and you didn't want to simulate an entire canopy, for example, because it's too computationally expensive, this is a nice way to get rid of those edge effects and just have your portion of canopy that you want to model to repeat indefinitely in all directions. So then you don't have this sort of edge of your canopy to deal with. I want to take a quick second just to talk about debugging so that we can practice our debugging skills. I would say by far the most common error with new users of Helios is specifying the wrong arguments to functions or methods. So let's just illustrate this. Let's say that when I was calling this rotate primitive method here, that I forgot one argument. So maybe this last axis, I just forgot about it. You're going to notice that it will complain. It will say no matching member function for call to rotate primitive. It says that we need at least 3 arguments and there were only 2 provided. Let's say that I didn't notice that, or I'm not using an IDE like this and I tried to run. It's going to give a similar error message. So it's going to say this method here, rotate primitive, has no overloaded function that takes 2 arguments. It's trying to match the argument list that we provided, and there's none available. And so then the question is, how do we know what are the types and numbers of arguments that we need? If we're in Sea Lion, it tells us here, we can click on these and it will link us to the source code where we can see the different options for this function. We can read the documentation here in the actual code. Another good thing to do would be to just go straight to the Helios documentation. We can come up to the search bar and type in that function, which is rotate primitive. And if we click on it, it will give us all the overloaded options. So let's just click on the first one. It'll take us to that part of the documentation. So we see we've got this one that takes an unsigned integer, a float, and a vec3. We can read about it, what each of those arguments are. Here's another option with an angle, an origin point, and then an axis about which we want to rotate. Here it says 4 of 6. That means that there are 6 different overloaded versions of this rotate primitive function. So you could read about the different ones, and then we need to choose one and make sure that we're consistent. We only provided 2 arguments, a vector of UUIDs and then a float value for the angle. And so we needed to provide an axis. And so it caught this because it violated the rules of C++ here. And so it caught it for us and gave us a compile time error. Sometimes you can get errors that are runtime. So let's talk about that real quick. Let's say when I was setting my source flux, I just mistyped here. Let's say that I just typed PA instead of PAR. This is perfectly fine as far as the compiler goes, because it's not going to evaluate this and check it to see if that was correct ahead of time. And so this will compile and run just fine. Sorry, it won't run just fine, but it will compile just fine and start to run. So let's go ahead and run this and see what happens. So we came up with an error. It's going to tell us that the error was in set source flux, and it can't add a radiation source for a band called PA because it's not a valid band. We didn't add it. So we kind of know that this was where it happened, but maybe our code's very complex and we don't know exactly where we made this mistake. Let's go ahead and run it in debug mode by pressing the debug option. This will give us some additional debugging information to help us know exactly where this is happening. Okay, so it usually automatically pulls up this assembly code. We can just clear out of that. What we want to go over to is the threads and variables. So this is going to give us the whole stack of all of the functions that were called in getting to our error. So if we come up to the top, we can start with our main. That's usually where the stack is always going to start. If we double click on this, then it will highlight where in main.cpp that error happened. And it happened right here. We could continue the stack if we wanted to just take a look. So the error then happened in the set source flux method. It does some error checking here, and it's throwing our error here because it wasn't able to find that band. It doesn't exist. So this helps us to know what our error is. If this was a different type of error, then we could, debug based on these values. You could set breakpoints, etc. So let me fix this here. Just one more debugging related point I wanted to illustrate. The calls to many of these methods can be done in any order when we're setting the parameters for our band. It's just important that we do those after the band has been declared and before we update our geometry and run our band. So for example, let's say that I was to move this line of code up one, and we're trying to disable emission for a band called par, but that band has not been declared yet. The band is not declared here, so when it calls this method, it's going to throw an error because it doesn't know about that band yet. It's running this in sequential order. So let's go ahead and run this again. We'll run it in debug mode. So we came to our error. I'm going to close out of this. You'll notice that when it immediately jumps into this debug mode, it's not going to give us our error message. You need to click on this console tab, and this will take us to our command line. So the error was when it tried to call disable emission, and it says it can't disable emission for band par because it's not a valid band. As we said, it hadn't been declared yet. We could go in our debug window and look at our stack, threads and variables. And you can see it happened in main on this line 18, as we would expect. And then it got into this disable emission. It was checking if that band existed, and then it threw an error. So that was our issue. The last concept that I want to illustrate is when you have multiple bands. We just had one band called par. There was nothing really special about it. We just kind of set its flux. And so there's nothing really that makes it par per se. But let's try adding a band called NIR, and then we'll set its radiative properties so that we get some actual scattering. This will distinguish it from our other band that, let's say, doesn't have any scattering. So we could just copy paste all of this code. Let me fix our error here that we created. So we could copy paste all of this again, and then just add it and change our name to NIR. A slightly more convenient way of doing this would be to call the copy band method, radiation.copy band, copy radiation band, and then we can give it the label of a previous band, the existing band, and then the label of a new band that we want to create. So we could do par is our existing band, and then our new band, let's call it NIR. Again, this is just a label that we made up. It could be any label that you want. We're just going to use that to reference it later. So now the thing that we're going to do to distinguish this is let's change the reflectivity of our dragon so that we get some reflection and scattering in our NIR band. And let's come back to our documentation here. So let's go back to plugins and radiation model. And we can look at the input primitive data that we can specify. So we can specify the temperature of our primitive. The thing that we want to specify is our reflectivity. So the way that we specify our reflectivity is via this primitive data called reflectivity underscore, and then the name of whatever band it is we want to set that reflectivity for. Usually our radiative properties differ between bands, and so here we're going to have reflectivity underscore par or reflectivity underscore NIR. You'll notice there are some other ones. There's our emissivity, as well as our two-sided flag that we talked about a little bit earlier. So let's set our reflectivity for the NIR band. So to do that, we'll set primitive data. So I'll add that up here. So let's call context.setPrimitiveData. And then we'll give it a vector of UUIDs for which we want to set the primitive data, UUIDs underscore dragon. And now we need the name of the primitive data to set. So we just said that was reflectivity underscore, and then let's do NIR. And then our last argument is going to be what that value is going to be. Let's set it to a fairly high value of, say, 75% or 0.75 so that we get a fair amount of reflection just for the sake of illustrating. Now there's one more thing that we need to do in order to actually get some scattering to occur. Right now, by default, we have no scattering iterations in our simulation. By default, that's just 0. And so nothing would happen as far as this reflectivity value because we don't have scattering enabled. We have to actually trace that scattered radiation. And in order to do that, we need to set our scattering iterations to be greater than 0. So for our NIR band that was just created, let's set that. So we'll do radiation dot set scattering depth. And our arguments here are going to be the label of a band and then the number of scattering iterations. So our band we want to do here is NIR, and then our depth, let's just take it to be 2. Let's leave our par band as a scattering depth of 0, which is the default. This is because we haven't changed our reflectivity, so there's going to be no scattered radiation to trace, so we might as well just leave it at 0. You could set it as 2 if you wanted to. The model would automatically detect that there's no radiation to scatter and skip it anyways. Now the next thing to change is we want to have it actually run our new NIR band. Right now we only have it running our par band. We could just copy paste this and have it run our NIR band after. This is going to be pretty inefficient because every time you call run band, it's going to do a separate ray trace. We can use a different version of this method in order to run all bands all at the same time so that we don't really incur much of a performance penalty when we add our additional band. And so to do that, we're going to instead pass a vector of strings to this instead of just a single string value. So let's make a vector of strings and we'll call it bands. And we'll say it's going to be equal to par, comma, NIR in quotes. So now we have a band here, and let's pass that variable to this run band method here. So now it's going to run both of these bands in a single ray trace. And the last thing we need to do, let's change our visualization so we're not visualizing based on par anymore. Let's change it to NIR so that we can see the effects of our scattering. And we can go ahead and run that. I won't run it in debug mode, I'll just run it in regular mode. All right, and here is our result. You'll notice two main things that are different when we added our scattering. You'll notice that the absorbed fluxes for our dragon are much lower. It's darker colored, so our fluxes are maybe closer to 100. The reason for that is because it has a very high reflectivity of about 75%. So before, where it may have been absorbing up to about 500 watts per meter squared, now it's going to be up to maybe 75% of that. You'll also notice it's a little bit faint, but you can see some scattered radiation that's being absorbed by the ground here. It's not this perfectly uniform yellow color anymore. You can see that we get a little bit higher values right next to the dragon where it's getting a lot of scattered radiation, and then it gets slightly darker as we get out here on the fringes. All right, that is all for this first lesson about the radiation model. Go ahead and subscribe if you're interested in our future videos going over the radiation model in more depth.